Okay, recording in progress. So today we're going to change things up a little bit. I know I said that Wednesdays would be lab day, but I wanted to finish up this material concerning at least what we're building towards from conditional probability to Bayesian probabilities, Bayesian statistics, because we're going to have an assignment, a future assignment, a project where we're going to use that and we're going to use pandas as the mechanism to do that. And so I'm going to go through kind of more theoretical material today, and hopefully, depending on how much of it we get done, maybe do some of the balance on Friday. But then I want to use after that 2 days for the following two class modules as practical assignments, practical portion. Okay. So we're going to change things up a little bit today. Question, yes. Oh, you do? Oh, I didn't know that. Okay. What is wellness? Well, I know what wellness day is, but like, okay, well, that's good. Hey, kind of like finding a dollar in the couch, right? Um, that's good. This Friday? Oh, hey, that means I don't have to prep for it. Okay. All right. That works for me. Thank you. Yes, question. It's getting there. Now, one of the things with Canvas that I didn't realize, it treats comments like text messages. And so that means I had to type everything in instead of, on the fly. So I have reams and reams of comments that I wanted to type. But what I start out with is I'll first put little sections in each person's comment, and it allows you to save drafts. But that draft, the only choice it gives you is to submit it so that you see it and not to edit it like they did in Moodle. So I'm still trying to figure out if there's a way to edit messages because it's uh, kind of a pain actually to not be able to edit your messages because I'll go through everybody's assignment a couple times so then make sure that I'm consistent in how I'm grading stuff like that. So to answer your question, not yet. I just have to figure out how the comment stuff works in Canvas because it treats it like text messages and not like an edit session. Okay. Any other questions? No? All right. So let me just last time when I taught this class, I didn't emphasize the Bayesian techniques, and it's really a category of techniques that are immensely useful for all sorts of applications, and will motivate that towards the end of this module, whether we finish it today or on Monday. Um, that's good to know. All right, I would have come in and been like, "Oh, where is everybody?" All right, so let me hide the floating meeting controls. But before we begin, some administrative bits. The reading has changed. And for the reading, what I like to do is to give you the reading before or kind of while we talk about the subject, right? So I always have the reading ahead of when I talk about the material. So the reading has changed in the Python book, Python for Data Analysis, Chapter 5, Getting Started with Pandas. And the book is I think it's well written, but it's certainly not the only source in the world for pandas. Pandas is very popular. And in fact, Wes McKinney, the author of the main text for the course, actively contributes to pandas. So this should be, if any sections of the book are really, really good, it should be those sections on pandas. All right. Homework number one will be pushed out. I already have it written up. I just have to spell check it because, as you probably know by now, my spelling is not as good as it should be. My high school English teachers would be very disappointed with me. But that being the case, homework two will be exercises just like we had last time, purposed with you getting practice with evaluating or enumerating complex events, as well as calculating probabilities. Okay, any questions? No? Anyone going away on Friday? No? Not gonna drive somewhere at least? Just gonna relax, sleep in? Okay. All right. So that being said, let's jump right in. So where we last left off, we talked about this idea of a filtering probability. And what we said, just like a regular probability, regular meaning probability for a random variable, we take as our proportion in our calculation the number of objects that are desired or preferred, the numerator of this expression, divided by the total number of items, our universe of consideration sample space omega. And so we went through this exercise, and in this exercise, the goal was to have multiple attributes associated with the objects under consideration, with the idea that a random variable takes some measurement over those objects. And you can think of it as almost reading off one of these attributes, decorating or associated with each one of our objects. And so we added this idea of filtering probabilities. Excuse me. With that, we had two attributes, and we so-called conditioned on the bin number attribute being 3. And we said when we do that, you effectively iterate through all of your objects, and you set aside those objects for which that condition random variable is equal to true. So in this case, if the bin attribute or bin number attribute is 3, you set aside those objects, the 2 greens and the 3 yellow tennis balls associated with that bin number 3. And so when you then evaluate the probability, the denominator of this proportion changes to be the cardinality of that so-called new universe of consideration. And that has the impact of making the denominator smaller. And as a result, the probability that you evaluate is going to be larger. With more information, your belief or your probability increases. Okay. And so the numerator is still, in this case, probability that the color is green, but this filter, this condition b equals 3, it changes that denominator. Okay, any questions about this? Question? No? Makes sense? Jar your memories from Monday. Monday seemed like such a long time ago. All right. And so we then went into the definition of what conditional probability is. And we said that conditional probability expresses that proportion for the co-occurrence of the two variables A and B relative to this new universe of consideration, the number of outcomes where we take our original universe, sample space omega, and shrink it down to only that portion we've set aside, namely those objects carved out associated with the event we're calling B. Okay. Any questions? Does that make sense? Yeah? All right. And so we talked about this idea of variable coupling, and I was waiting so much to throw in a Lionel Richie reference in this class, but we talked about this idea of variable coupling. And with that, we said covariance and the normalized version correlation is an expression of linear dependence between random variables. Now, that's not the only measurement of dependence, because as we saw with the conditional probability, when you say I'm given B, if there's a relationship between B and that variable A, the probability is going to change. It gives you information. Knowing something about B tells you something about event or random variable A. And so suppose, we'll just kind of warm you up with this. You have two events, and you have random variable A, and random variable A measures the price of coffee at Clark University, which is overpriced, just is. And random variable B is measuring the price of tea at Tufts University, where I went for undergrad. Now, if I were to ask you, do they have some relationship to one another? Well, do they? No, they don't? Okay. Well, certainly they don't. I promise you that they don't. Now watch them use the same vendor and the prices are impacted, but that's a whole other conversation. But nonetheless, at face value, these two measurements, A and B, or random variables, have nothing to do with one another. And so this idea of coupling is related to conditional probability, that if two measurements are not coupled or linked together in some way, a change in one means a change in the other, and they go hand in hand. If they're not related to one another, that's almost like saying when you condition on it in the conditional probability sense, it does not change the probability. And so this idea of coupling related to conditional probabilities is statistical independence. And that's another way of talking about the relationship or the coupling between measurements or random variables. Okay, any questions about this? Make sense? All right. And so oftentimes, well, I'll get into what independence is. And so more generally, two random variables, A and B, are independent if the probability of their joint or co-occurring occurrence, probability of A and at the same time B, is equal to the product of their individual occurrences. And so we have probability of A and B is equal to the probability of A and the probability of B. So what that means is knowing one event, like say given B, doesn't really tell you anything about the other event, event A. They share no information. Now, this means that when they co-occur, their co-occurrence, that rate or that probability defining when that co-occurrence happens, is calculated by the individual occurrences. That's what the product of the individual probabilities means. And so this is a definition of independence, but it's more than that, right? And I'll explain what I mean by that from the perspective of joint probability. Now, oftentimes when this is typically discussed, they show you the Venn diagram and they carve out those objects from our sample space, omega, corresponding to the A event and the B event, and they draw them non-overlapping. Okay, if they're non-overlapping, their co-occurrence, because they share no information, their co-occurrence is exactly the probability associated with each one occurring separately. They're not linked together. So knowing something about B doesn't tell you anything about A. Okay, does that make sense? Any questions? And so independence in this alternate definition expresses exactly that. If we are given event B, the probability of A is exactly the probability of A. And so like we saw with the balls and bins example, the probability of a certain color started out as 20%. And when we were given the bin number, it went up to 40%. But in this case, if we conditioned, if they're independent, conditioning on B wouldn't change the probability of A. Does that make sense? All right. And so this idea of independence, if we expand out just what our definition of a conditional probability is, so probability of A given B is the joint occurrence probability of A and B at the same time divided by probability of B. Now, if we assume they're independent, the joint occurrence or the concurrent occurrence of A and B is just the individual or the product of the individual occurrences, probability of A times probability of B. And so now we have a copy of probability of B in the numerator and in the denominator, and they cancel, goes to 1, and we're left with the probability of A, okay? And so we know mathematically this works, but if we think about it, and I really want you to have the visceral understanding of what statistical independence means. If you think about it, here we have the intersect region, probability of A and B, divided by probability of B. We're expressing that ratio. That's what this conditional probability is. If it's equal to the probability of A, that's the set of objects corresponding to the A region carved out of our sample space, divided by the original universe of consideration. And so what this means is that this proportion, intersect region over the B region, is equal to the same proportion as the A region over the original universe. Does that make sense? So this is just an interpretation of what this expression, probability of A and B over probability of B equals probability of A, what that expression means. Okay, so let's take a look at what happens. Now we're going to draw the Venn diagram, and in this configuration, we have object A or event A and event B are non-overlapping. If they're non-overlapping, the count of the number of objects in our universe in the intersect region is going to be 0. And so if we talked about A and B, that probability, that's going to be 0 in the numerator. And for the B region, B is going to have some count. Okay, so it has a probability that's going to be equal to 0. Okay. Now, if we compare that ratio, intersect region over B region, to that other proportion, A region over the universe, 0 is going to be less than, unless A is 0, but most of the time it's going to be less than that probability of A, which is the objects in the A region divided by the objects in the universe. Does that make sense? All right. So now let's push these events together. And imagine they just barely start to overlap. And because they just barely start to overlap, now that intersection region where both A and B occur jointly is going to be non-zero. And because it's non-zero, now the numerator for this first proportion, intersect region over B region, it's going to be a small number. Okay. Now, if it was 0 and it just started to become non-zero, for the most part, it's still going to be less than this other proportion, the amount of objects in the A region divided by the number of objects in the universe. Does that make sense? Any questions? No? So let's continue to make this intersect region bigger and bigger and bigger. And at some point, you make it big enough that these two proportions are precisely the same. That the intersect region over the B region is exactly equal to the proportion of the A region over the universe. Now, of course, they're the same in this case, but if we continue to make this intersect region even bigger, if it used to be equal, the proportion on the left to the proportion on the right, if we make it this intersect region even bigger, the numerator is going to get bigger for that intersect region. And therefore, that particular proportion, intersect region over B region, is going to become greater than probability of A, the A region over the universe. Does that make sense? All right. So that means if we hit the right amount of overlap, the size of this intersect region, we can get sometimes, not all times, but we can get this proportion, intersect region over B region, to be exactly the same as this ratio A region over the size of the universe of consideration. So if we hit the right amount of overlap, it makes no difference to the proportion about knowing B, and that's what independence means. It doesn't necessarily mean they're not overlapping. It means the proportions are the same. Does that make sense? And so when we say adds information, we mean this idea in the Bayesian interpretation, belief. Our belief does not change, knowing this piece of information, where belief is this percentage, this proportion, namely our probability. Okay. Does that make sense? Any questions? No? All right. And so an independence example, and I just made these numbers up. Suppose we have two events. The probability of A is 0.3, and that's the entire A region carved out of our universe of consideration. And again, as a probability, it's the number of objects in A divided by the number of objects in the universe. Probability of B is 0.4, and in this case, they're overlapping. Now, I'm repeating this idea of one way of expressing independence. It says the joint occurrence is defined by the individual occurrences. There's no information there. One event, knowledge of one event, doesn't tell you anything, doesn't increase your belief about the other event. So if they are independent, okay, that means the probability of this intersect region is just the product of the individual occurrences. Their occurrence of A, some value, is by itself, and the occurrence of B at some value is by itself. There's no coupling there. And so if we multiply the two, we get the probability associated with this intersect region is 0.12. That's just 0.3 times 0.4. And if that's the case, we can do a little bit of algebra and we can say, okay, well, if we know A is probability 0.3 and this overlap region here in the center is 0.12, that means everything that's in A but not in B, all right, what's left, is 0.18. right? Likewise, we can calculate everything that is in B but outside of A. That's probability of not A intersect B is 0.28. We arrive upon that by taking our 0.4 and we subtract out that overlap region 0.12. Okay, any questions? Does that make sense? All right. So now, and just for good measure, everything else outside of A and B is 0.42. And so if we were to look at this expression, not A and at the same time not B, well, that's the same as saying A union with B, and then we take the complement. A union with B is this region, so we take, here's A, here's B, and imagine if we picked all the objects that are common to both, everything that's outside of that is not A intersect not B. But nonetheless, let's take a look at this idea of the intersect region over the B region being equal to the A region over the universe. And so here, intersect region over the B region, well, the intersect region has a probability of 0.12. That's what we calculated. And the B region has a probability of 0.4. If we divide them, express that ratio, it's 0.3, which is exactly what our proportion was for that A region. Right, does that make sense? And so that means that event A and B are independent. And so independent doesn't always necessarily mean they're non-overlapping in the Venn diagram. It says that the proportion, your belief doesn't change when you know this piece of information, when you condition on it. Does that make sense? All right. Any questions? And so there's a property, and I hate to have a proof in this class, but there's no other way to really convince you that this works, that if you have two events and they respect this idea of conditioning does not add information, their complements are also independent. So what it means is that if we have a situation where we have A and we have event B, if A and B are independent, okay, that means that everything outside of A and everything outside of B, that means the complement of A and the complement B are independent from one another. And so if we take A, there's its complement, everything outside of A in our universe. And if we take B, there's B, everything outside of it, that those two sets are also independent. Okay. And so it's not so intuitive. So let's just go through that proof. So in this, whenever you take the complement of something, intersection is the same as overlap, but union takes all of the objects in one set A and it puts them in the same set as the other set B, but everything that is common to both, you only get a single copy. So it's the bringing together of two sets of things, but you only have one copy of each object. And so whenever you take the complement of the union, well, here the A turns to A bar, the B turns to B complement, but union turns to intersection whenever you have a complement, okay, mathematically. All right, so that being the case, well, let's start out with our complement of A and at the same time complement of B. So A bar complement B bar. And we're going to make the assumption that A and B are independent from one another. Their joint occurrence is just the product of their individual occurrence. There's no statistical coupling between the two. Okay, everyone understand so far? Does that make sense? No? All right, yeah? All right. So now, okay, we're going to rewrite this and we're going to say, okay, well, not A intersect not B complement is the same as A put together union with B, and we take that result and take the complement. That's just a mathematical fact, and we'll rewrite this. So if we say A union B, its complement, we refer to, here's A, again, here's B, A on the left, B on the right, The union represents all of this space carved out by both A and B. And then the complement is everything else outside of that combination. And so if we do that, well, that's the same as saying 1 minus the probability of the union. And the reason why that works is because the probability of the anything event, our sample space omega, is always equal to 1. So if you want the probability of a complement of any event, that's the same as taking the probability of everything that's left after you carve out those objects. And we start out with a probability of sample space omega being 1. So by subtracting that event from 1, we get the complement of that particular event, A union B. Does that make sense? All right. So now, okay, using that fact, now we're going to take our expression for the union of events A and B, and we're going to write out the probability of that particular event. Now, you're going to use something called the principle of inclusion-exclusion. And what that says is that if I'm computing the probability of two overlapping events, we have event A on the left, and we have event B on the right. Well, if you take the probability of A, that's the probability of this region, okay? And if you take the probability of B, well, that's the probability associated with this region. But you'll notice that the overlap was counted twice. So you have to fix that up by subtracting one of those copies, because you have the probability of A. Let me just kind of draw A. You have the probability of B, right? And there's the overlap region here, overlap region. You've counted this overlap 2 times. And so how you fix that up, oops, is you subtract out one of those copies of the intersect region. Okay. And you can do something similar with probability of 3-way unions, 4-way unions, arbitrary way unions. And so if that's the case, then we rewrite the probability of this union between A and B, probability of A plus the probability of B, subtracting out that doubly counted intersect regions probability. Does that make sense? Any questions? No? All right. So now, okay, let's make another substitution. Now, probability of A, if you have the probability of an event, we just said it's the same as 1 minus everything that's not in that event. So we're going to make a substitution here. We're going to say, okay, everywhere we see the probability of A, we're going to write that as 1 minus everything that's not in A in terms of the probability. Everything that's not in A is this shaded region. And if we take the probability, 1 minus the probability of everything not in A, that's exactly what's left is the probability of this A region. And so we can make that substitution both for A here. We see this first term, probability of A. We can also make that substitution for the second term, probability of B. So we're just using that fact called total probability to rewrite what it means to be the probability of A and what it means to be the probability of B. Okay, does that make sense? Yeah? All right. So now we're going to do that. And here, this first term, that used to be probability of A. This second term, that used to be probability of B. It's the same value. We're just rewriting it, a synonym for it, as it were. And this last term, this third term here, we just said A and B being independent, their co-occurrence is the product of their individual occurrence, implies this fact. So we make this assumption everywhere in our proof. And for that reason, here we have probability of the co-occurrence of A and B. So we're going to rewrite that just as this product, and that's from our assumption. Because we're setting out to prove that if A and B are independent, that means that complements are also independent. Does that make sense? So that's a legal substitution that we can make. Okay. So now, make that substitution. Let's see, where'd I go? We'll make that substitution again. So here, we have the probability of A. We'll call that our first term. Probability of B, call that our second term. So when we go down below, okay, there's our first term, substituting that fact. Probability of A is 1 minus the probability of complement of A, and we make that substitution for that second fact. Does that make sense? All right. So now, and I promise you, everything will cancel out and converge down to the result. We're going to use the FOIL rule. And so when you learned a long time ago multiplying factors to make a polynomial, or you factored a polynomial, you learned the FOIL rule, right? First outside, inside, last. Or you learned you multiply the first term, second term, and the cross terms if you had a more linear algebra treatment of it. But that being the case, we're going to multiply these two terms. And with these two terms, we're going to apply the FOIL rule. So we're going to multiply the first term with the first term. We're going to multiply the second term with the second term. And then we're going to add to that the second term here times that first term. And then we're going to add to that that first term times that second term over here, right? And so this is just an application of the FOIL rule, okay? So if we do that, okay, well, 1 times 1 is 1, right? So we took care of these two. We have 1 times minus probability of B bar. So that's this term. So it's the first term, this is the second term. And then we have minus probability of A bar times 1. That's the third term here. And then lastly, we have this times this. That's that last term. They're both negative, so that sign becomes positive. And we have probability of A bar times probability of B bar. And that's our fourth term. Okay, any questions? Make sense? All right. So now, okay, well, let me rewrite that up at the top, make it a little bit cleaner. And we'll notice here, this parenthesized expression that we have has a leading negation. So that's like multiplying by -1. We're going to distribute that multiplication over the terms in the parenthesized expression. And so this is going to become negative. That's going to become positive, positive. That's going to be negative. Okay. And we're just going to redistribute this negation to every term in that parenthesized expression. So we do that, and okay, we have what we had before. This does not change. We have a -1. Okay, -1 down below. We have a positive probability of B. Okay, that's taken care of. We have a positive probability of A bar. And then we have a negative probability A bar times probability of B bar. Does that make sense? Yeah? All right. So now that we do that, this is where the magic happens. Not really magic, just algebra. So we have here a copy of probability of A bar and negative copy of probability of A bar. Anything added to itself is 0. We also have a copy of probability of B bar with a negative copy probability of B bar. So those are going to cancel, go to 0. Here we have a copy of +1 and a copy of -1. So that's going to cancel. And then we're left with here 1, this term 1 minus the product of probability of A bar with the probability of B bar. So let's rewrite that. First, any questions? So we cancel out mostly everything. And now we're left with this simple expression. And we just solve for that. And we have 1 minus 1. And we have a positive product probability of A bar times the probability of B bar, which is exactly what we were after. Okay. Any questions? And so if two variables are independent, the joint occurrence is just the product of the individual occurrences. There's no information coupling statistically between them. You can go ahead and safely assume that if two variables are independent, then their complements are also independent. And it's not quite clear from the Venn diagram why that's the case, but certainly mathematically that is the case. Okay, any questions? Does that make sense? All right. And the reason for this is sometimes when you're dealing with practical problems, it's easier to think of the complement of something than the positive sense of some event. It's a very helpful tool, in fact, for this type of system. All right. Any questions? No? All right. And so this idea of Bayes' rule makes use of conditional probability. And we talked about the definition of conditional probability. Probability of B given A is the joint occurrence over probability of A. Likewise, we can write probability of A given B, again, as the joint occurrence over the probability of B. That's just an expansion of the definition. Now, one of the facts that we have is this and function, this intersection, it's commutative. It doesn't matter if you have A first or B first. And so A intersect B is precisely the same as B intersect A. Now, if that's the case, we can certainly take both of these expressions. Let's call this our first expression. Let's call this our second expression. And we can rewrite the numerator so that the A and the B are in either direction, right? Make sense? All right. So let's go ahead and let's use that fact. And in this case, we've taken probability of A given B, or rather B given A, and we've rewritten the numerator because we know that intersection is commutative. Now, I always like to, every time I see A given B, I always like to write in the numerator the same order on the intersection. But it doesn't really matter what order you write the intersection in, because intersection or and is commutative. Okay, so now we have the same expression for equation number 1 on the left and equation number 2 on the right. So now we're going to do a little bit of algebra. For the equation on the left, we're going to multiply both sides of equality by probability of A. Okay. For the equation on the right, we're going to multiply both sides of equality by probability of B. Now, if we do that, okay, we have a probability of A on this side. We have a probability of A on that side of equality. These cancel. Likewise, if we multiply probability of B, both sides here for equation 2, probability of B in similar fashion, we have a copy of probability B in the numerator and denominator, it goes to 1. So if we do that, we're left with the following. We have the probability of B given A times probability of A is equal to the joint occurrence. Likewise, the probability of A given B times the probability of B is also equal to the joint occurrence. So we have, for this transformation, you'll notice for both equation 1 and equation 2 on the right-hand side of equality is exactly the same. So if the right side of equality is exactly the same, these two expressions mean the same thing. So we can equate the two to one another. Does that make sense? Any questions? Yeah? All right. And so this expansion has a name. It's called the product rule. And what this product rule says is that if you want the probability of a joint occurrence, that probability of the joint occurrence is the same as the product of the condition times the single variable. And this is also sometimes called a factorization. If you think about probabilities, this probability, the joint occurrence, on the right-hand side involves two variables, A and B, as the thing you're trying to calculate the favorables over. And this has a single variable involving A, and this one is a single variable B, but you've changed the universe using this A. And so in each case, we go from a probability that favorable over two variables to the product of favorable over one variable on the left-hand side. And so like a polynomial, you take a complex expression and you break it down into the product of simpler terms. And that's exactly what this product rule is doing. It's saying you can redefine this favorable in terms of two variables into the product of simpler probabilities, favorables involving just one variable at a time. Does that make sense? Any questions? No? No questions? All right. So now that we have two different ways of writing this joint occurrence, probability of A and B, we can equate them together. So if the two right-hand sides are the same, which they are, we can equate together the two left-hand sides. Does that make sense? Yeah? All right. So now we have this expression, and we say probability of B given A times probability of A. That's the left-hand side of equality here. And we have on the right-hand side probability of A given B times probability of B. That's the right-hand side of equality. Okay. And so now we're going to do some algebra with this expression, we're going to divide both sides of equality by probability of A. So we're going to divide over here by probability of A on the left-hand side, and we're going to divide on the right-hand side of equality by probability of A. Okay, so we have a copy of P of A, both in the numerator and denominator that goes to 1, and we're left with probability of B given A is this probability of A given B times probability of B upon probability of A. Does that make sense? So it's just algebraic operations. All right, and so this expression has a name, so-called Bayes rule. And what this Bayes rule does is connects two different conditions. On the left-hand side of Bayes rule, we have given A. It says, if I observe an outcome of variable A, but on the right-hand side, the observations are in terms of variable B. Now, this idea of conditioning, it says you can effectively manufacture as if you saw or observed A with things that you already have observed. And even if you've never observed an instance of variable A, you can kind of construct the same value as if you saw A. And it's immensely useful if you have one piece of information and you want to evaluate a probabilistic question, what is my belief about this, with other information that you have. And it's used all over the place for classification and robotics, clustering, lots and lots of applications, prediction, you name it. Okay. Any questions? That makes sense? Yeah. All right. And so an example, Bayes rule, and this is you'll see lots of examples like this, but the actual numbers would come from, in this case, FAA information. They collect lots of statistics about arrivals of flights and departures of flights and things like that. So let's imagine you have 90% of your flights, they depart on time, leave the airport. 80% of your flights, let's assume, arrive on time. And let's imagine 75% of flights both depart on time and arrive on time. Now, based on weather conditions, how much air traffic is near an airport, just because you depart on time, it doesn't mean you're going to arrive on time. You might take longer in flight for various reasons. And so let's define two events, A for arrive on time, and the other variable D for depart on time. Now, by the specification, we have 0.8 probability for random variable A for the arrival. We have 0.9 probability, 90% for depart, as defined by the specification. And then the intersection probability of arrival and departure at the same time, on time, those two events occurring together, is 0.75 for 75%. Okay, so now if we wanted to know, for example, what's the probability that a flight arrives on time given that it departed on time? Okay, that might be a reasonable question you want to ask. So here, again, we give our expansion for conditional probability. We have the joint occurrence in the numerator, and we have the probability of depart on time in the denominator. We plug in, and we get like 83 1/3%. Okay, you might want to know, given the probability that given that it arrived on time, what is the probability that it departed on time? That's another question that you might want to ask. Again, we give our expansion for conditional probability. We have the joint occurrence in the numerator, and we have the probability of arrival in the denominator. We plug in our numbers. We get about 93 3/4%. Okay, does that make sense? Any questions? So we're just plugging. Yes, yes. The individual probabilities are 0.8 and 0.9, and the joint. So if we were to look at the overlap region, and that's a great question, this is 0.75, and if probability of A is 0.8, then this region would be 0.05, and then this region, that part of B that's not in the overlap, would be what, 0.9, 0.75, 0.05, so 0.585, 9. So that'd be 0.15 here, right? And so that's just the relationship between them. And if we know this is probability of that is equal to 1, right? You could certainly compute what this space that's outside of the union is. And so, and I'm glad you asked that. These express the relationship between these two events and how they overlap, but not, it still adds up to 1. Okay. Any other questions? No? All right. So now, to show you the Bayes rule works, we're going to compute the probability of departure on time given the arrival on time. But we're not going to do it directly using the definition of conditional. We're going to take advantage of Bayes rule. And so plugging in Bayes rule, D given A is equal to probability of A given D times probability of D over probability of A. It's exactly our expansion of Bayes rule, but we're plugging in the D variable here in the role of the B here in our example, and the A variable in the role of the A here. And so given this, well, probability of A arrival given departure, we calculated that. That's 83 1/3%. Probability of departure on time, that's 0.9. And then in the denominator, probability of arrival on time, that's 0.8. If you do the calculation, it's exactly 93 3/4%, which is exactly what we had here. But the difference is we synthesized as if we knew it was arriving based on knowing that it departed on time. Okay? And any questions? That makes sense? So Bayes rule really is a thing. And here, rather than requiring an observation given A, we construct it from a different observation given D. Okay. And so this last one, total probability, is a really important tool. And I'll probably end with this because I want to make sure everyone understands the construction. And this total probability combined with Bayes rule is the complete formulation of this Bayesian approach. Okay, so suppose you have your sample space omega and you're going to partition it, kind of like a Sicilian pizza. And if you want what I think is the best pizza in Worcester, Worcester's best pizza, or sometimes it's called Frankie's pizza, really, really good pizza, I think. And I drive a half an hour to get it. But nonetheless, you have a Sicilian pizza, and imagine this for your sample space omega, and you're going to chop it up into slices, and these slices are non-overlapping, and it completely partitions our sample space omega. Okay, so now we're going to give a name to each slice. That first slice we're going to call B1, right? That's our first partition. And our next slice we're going to call B2, B3, etc. And we have K many slices. It doesn't matter what K is, but what matters is these slices are non-overlapping, right? Okay. And so an arbitrary two slices, if we wanted to compare them to one another, we would call one of them B sub I and the other one B sub J. And it doesn't matter what I and J is, but it just gives us a way to say, take two slices in order to make a statement about the relationships between slices and one another. Does that make sense? Any questions? No? All right. So now let's imagine that all of the slices, they're non-overlapping, and we can put them together in a union, combine all of the objects that they carve out of our sample space omega. And if we combine all of the slices, that completely covers all of the objects that comprise our sample space omega. So the term for that is collectively exhaustive, right? It completely exhausts as a collection all of the objects that form our sample space omega. Okay. Likewise, for any two slices, Bi and Bj, and let's make the assumption that the two slices are not the same. So I is not equal to j. For any two slices that you pick, if we try to take the intersection between them, that intersection is 0. And so no two different slices carve out of sample space omega the same set of objects. Their intersect region, their overlap region is 0. Okay. Now that's called pairwise independent. Sometimes it's called mutually exclusive. They're independent in the same way that we talked about that Venn diagram, where these two events, A and B, were non-overlapping. That's one way people try to visualize independence. And so we have these partitions, this tessellation of our sample space, and this tessellation is mutually exclusive and collectively exhaustive. Now, when you have those two properties, that way of chopping up our sample space, any event, arbitrary event, let's call it A, that you can define on that sample space, each one of these slices gives you a principled way that you can use to construct any event that you can imagine. And if we take a look at this tessellation, we see that there's a portion of A up here in that slice. And imagine if we were kind of draw it like that. There's a portion of A in that slice below. There's a portion of A kind of over here. There's a portion of A over here. There's a portion of A over here. There's a portion of A down there. There's a portion of A that kind of looks like this, a portion of A that looks like this. And so that means that if your tessellation is pairwise independent, collectively exhaustive, you can use those slices to construct any event, regardless of what that event is. Now, the beauty of this is you can, in a regular way, decompose your event A, or any event that you can define. So what this means is that if I want to define A, another way of defining it is by taking the union of all of those pieces that I just showed you and put them together. Take all of the objects carved out in each one of those pieces where A intersects each slice and put them together. Okay. Any questions? Does that make sense? Okay. So mathematically then, it says, if I take A and I intersect it with each slice, for the first slice, second slice, all the way up to the kth slice, it doesn't matter what A is. What matters is that these slices are collectively exhaustive and mutually exclusive. Because here we see that B sub K, for example, the intersection of B sub K with event A, it doesn't have any events. It's empty, right? But those that are non-empty will give you all of the objects that collectively define A. So that means any event A, complex event, I can define it as a decomposition of the intersection with all of my slices and that original event A. Does that make sense? All right. So more compactly, I have a summation, and the probability of A, I can add, and unlike that principle of inclusion-exclusion, because none of these slices overlap, I don't have to worry about double counting those objects carved out of the universe of consideration where they overlap, because they don't overlap. Okay. So said differently, the probability of any event A is then just the sum of the probabilities of all of those intersects of each of the slices, and there are k many of them, those intersects of the slices with my object A, with my event A. Does that make sense? Okay. So that means everywhere I see a probability of some event, I can always define it equivalently as this summation. And it doesn't matter how many slices I have. I could have 2 slices, I could have 100 slices. It doesn't really matter. Okay. So now we can make this substitution, and that's where the construction comes from. It's from this idea of total probability. I have my partition over the entire sample space, and because of this mutually exclusive and collectively exhaustive, I'm guaranteed that I will cover any event in this representation. Does that make sense? Any questions? No? All right. So this partitions event A, and we can now take this intersection and we can rewrite it using the product rule that we had before. Now recall, we said for the product rule, we said probability of A given B is equal to the probability of A and B over the probability of B. If we multiply both sides by probability of B, we can say probability of A given B times the probability of B is equal to this joint occurrence probability of A and B, right? So anytime we see this intersection as a probability, we can substitute in from the product rule the conditional times probability of B. Does that make sense? So it's just a substitution, okay? So knowing that, okay, let's take an example. Suppose we had two slices. The first slice we call B. Let's say this half was our B slice. Everything that's not the B slice is going to be B bar, B complement. So that means probability of some event A, regardless of what it is A given B times probability of B plus probability of A given B bar times probability of B bar. I could have said B1 and B2 and written the same expression, okay? So that's an example of the degenerate case on the boundary value where you have two slices. Now, of course, it's kind of silly if you say you have one slice. You're not slicing it at all, right? All right, any questions? No? All right. So now, okay, you could rewrite this again if you wanted to write it using product rule as an intersection. Probability of A is the intersection of A with that first slice and A with that second slice, right? The two expressions are the same. So now this is our full treatment of Bayes' rule. Now, Bayes' rule, recall, it had in the denominator, in this case, we said probability of B given A is probability of A given B times probability of B. And in the denominator, I had probability of A. So all I'm doing is I'm substituting for this denominator with this idea of total probability. Okay. Any questions? No? All right. And so with that, well, how in the world do we get that? So this is our conditional probability, okay? And our conditional probability in another treatment, we can use the product rule and we can take this intersection and express it as these two simpler factors, A given B and probability of B. And then we take our denominator and we substitute for total probability, which is exactly this summation that we talked about here in our original treatment of the construction. And then we can now take this intersection and we can apply the chain rule and change it as the product of the two simpler factors. And so this full treatment is exactly what Bayes' rule says. Now, let me kind of unpack this a little bit. If we had two slices, this denominator I've written out using the substitution up here, but let's go ahead and just write out what we have here. We essentially, it says we can manufacture a condition. This condition here starts out given A, and you'll notice here on the right-hand side that every time we have a condition, it's always given B or B bar. And so we can manufacture a condition given A using a condition that we might have seen if what we've seen is different from what we want. Okay? Any questions? Does that make sense? And we'll have an exercise for this with data frames. Okay. And so you might be thinking, because I thought the same thing when I first heard this stuff, who cares, right? Well, it's a valid thought. Now let's go back to our yellow labs, right? Or is that golden retriever? I think that's yellow lab. One of the two. I confuse them all the time. And so with this, we talked about a set of variables, length, width, height, weight, and coat. And the instantiation of this random vector represents collectively the co-occurrence of one instantiation represents a particular dot as described by these measurements. And so here we said that when we have a conditional probability, you can treat either the condition or the variable of interest, sometimes called the query, either as a single random variable or a set of random variables that occur concurrently or occur jointly. And so in this case here, I've rewritten the expression for Bayes' rule here, the full expression using total probability. And now I'm going to treat here this B term, our query, that's going to be the coat variable. And then this A term here, my condition, I'm going to condition on the co-occurrence of length, width, height, and weight. Okay. And so if I do that, if I plug into Bayes' rule, everywhere I would see an A, my condition, on the right-hand side, I'm going to plug in the anding or the intersection between L, W, H, and M. Does that make sense? And so this Bayes' rule works for single variables, but it also works for the joint occurrence of a set of variables. Now, I just chose those as my condition, but I could choose any arbitrary. I could have probability of C comma L, C comma L given W, H, M. I can treat arbitrary collections of variables as my query, which is on the left-hand side, and my condition, which is on the right-hand side of the condition bar. Does that make sense? So why in the world would I want to do that? Okay, well, if I expand it out using Bayes' rule, I get the following expression. And now, if I, for example, said, give me the probability that a coat is shaggy, given these other measurements of length, width, height, and weight. Okay. And so what can I do with that? Okay, well, I can make predictions. If I don't know what the coat is, but I have these measurements for some dog, it'll tell me which one of these conditions or outcomes of the coat variable has the highest degree of belief, right? So that's prediction. So here we'll notice on the right-hand side, we'll give some names to these things. On the right-hand side, this term, oops, this term in the numerator on the left-hand side is called the likelihood. And that likelihood you calculate from your data. Here it says probability of this set of measurements given that the coat is shaggy. So what do? You segregate your data. You partition your data. You set aside all of those individuals where the coat is shaggy, and then that changes your universe of consideration. And then you count the number of occurrences where you have these measurements from what you set aside. And then the probability of shaggy, okay, you count how many are shaggy and how many are not shaggy, and that's how you calculate that term. Now in the denominator, and that's called the prior, the denominator is the normalizer, and the normalizer gets this to act like a true probability. On the left-hand side, that's called the posterior distribution, the probability of shaggy given that measurement. And so you get a data set with a lot of measurements of dogs. You get a new dog, you make these measurements of length, width, height, and weight, and then it'll tell you what the coat should be if you didn't know what that coat is. And so sometimes they drop the normalizer, and in that case, they say the posterior distribution is proportional to, that's what this symbol is proportional to the likelihood times the prior. Now they say proportional to, not equal, because it's not equal. You need that normalizer to make it a real probability. And so what you do then is you express this condition, probability of shaggy, of the coat being shaggy, given that measurement, probability of the coat being smooth, given that measurement, probability of the coat being medium, given that measurement, for all of the outcomes of that coat measurement, that coat variable. And then whichever one has the highest probability, the highest outcome, that's going to be your prediction. And so in this case, if smooth had the highest probability, you're going to say, aha, for this measured dog, the coat is smooth. And this is your largest degree of belief, because given your data set, this is what you most reasonably expect to see. Does that make sense? And so the beautiful part about this framework, it doesn't matter which variable or variables you have as your query on the left-hand side of the condition bar. It doesn't matter which variables you have as the condition on your right-hand side. You can calculate that using everything you know from your data set by filtering, right? You take your universe of consideration, you scope it down based on the condition, and then you count your favorables for whatever the query is. And you can manufacture any kind of probability without even necessarily having evaluated. You can even say, what if my weight was a certain value, my length was a certain value, how would my coat be, right? You can ask arbitrary questions of your variables using this Bayesian framework. Okay, any questions about this? No, does that make sense? And so it's a really powerful mechanism. And when we talk about data frames, we'll have opportunity to count these favorables and to change our universe of consideration using the filtering function that Pandas affords us. Okay, any questions? No? So that's why you should care about Bayesian statistics. It's very useful, and you can actually make a really nice career out of Bayesian inference, the answering of questions using these techniques based on data. Any last questions? No questions? No? Okay. So with that, that's all I had. Please look out for the homework to be posted. I'll post it as soon as I get back to my office. Unfortunately, office hours have been killed because I have an interview with a math faculty candidate, and computer science is hiring. I have an interview with a computer science faculty candidate, and she's going to be giving a talk, Dr. Heidi Ellis, at 3 o'clock in Sackler 121. I highly encourage you to go see it if you're not already among the students who's going to be meeting her for lunch. She's a senior candidate for being considered for hiring in the computer science department. So it's really important you make your voices heard. So question. I'm sorry. Why is it? Because we had a break from the practical, the project work, and I like to intersperse project work with the written. So the written homework is to exercise some of the stuff that we talked about, complex events and things like that. And then we're going to have another project with Pandas to kind of implement some of these things like complex events and favorables and conditionals. It's going to be more mathematical. So it's kind of like the exercises that we talked about, but it's not the same questions. Right? Sorry? No, no, no. It's going to be electronic. I'm completely electronic. In my previous institution, where I spent 11 years, we pivoted to all digital 2 years before COVID hit. So when COVID hit and we shut down, it was like a nothing burger, so to speak. But that being said, I like digital because it allows me to archive. Gradebook is my kind of saving grace, and it allows you to always know how you're doing. I just have to figure out on Canvas how you actually, compute the, 5% of this and 5% of that. But to answer your question, it's going to be all digital. And I'm glad you asked that. There's one point I wanted to make. Don't spend all your time figuring out equation editors. I'd rather you spend your time on the concepts. And so write neatly and then scan in your document, scan in what you've written, and keep it in a PDF, put it in a PDF on Microsoft Word, and that's sufficient. My old eyes can't read hieroglyphics anymore, but don't spend your time trying to get math equation editor and LaTeX to work. So write it by hand neatly, scan it in, and hand it in that way in a single document, and that's perfectly acceptable. Okay. Any other questions? No? Well, I'll see you on Monday. Hey, enjoy your Friday.